with our HL mock question 9, last one. We've got an alternating current generator with a rectangular coil rotating at constant frequency, and we're asked to explain by reference to Faraday's law of induction how an EMF is induced. Okay, so I've gone through to my data book. I've found the relevant equation. It's this one here. So epsilon equal to minus n delta phi over delta t. Okay, here we've got both Faraday's law, that's the proportionality to rate of change in magnetic flux, and Lenz's law, which is the minus sign. So just remember both of those for future references. Now, in this question, you're asked to refer to Faraday's law of induction, so it's definitely a good idea to be sort of thinking about what's in that equation when you're answering, and kind of fleshing it out with a bit of an explanation. Now, the bit that no one gets, or that no one really states explicitly, is this one. Okay, when we've got a coil in a magnetic field, that means that there is magnetic flux in the coil. And I'm going to draw a little box around flux. Okay, if I'm allowed to. Reason being is that often the word that is used wrongly here is field. Be careful. In this situation, the field is not changing. However, the flux is changing. And so any answers that are trying to kind of explain what's going on here must refer to the rate of change of flux, not to field. And unfortunately, IB is quite brutal with this. If you don't know your field from your fluxes, then you'll probably end up with a very low score for this answer. So in that case, however, there's quite a nice thing, which is we're kind of just looking at you just to give a very explicit statement, which is that there is some flux through the coil, and that will get you a mark. We then see that as the coil rotates, the flux through the coil will change, okay, and that's our delta phi over delta t. Let's then refer to Faraday's law. Faraday's law states that the EMF is directly proportional to the rate of change of magnetic flux, meaning that we will produce a non-zero EMF. So you notice here is a 3-mark question. Whoops, terrible underlining there. We've got a statement, very simple statement about the situation, that there is magnetic flux. That flux then changes. Well, if we've got a changing flux in the coil, according to Faraday, we must have an EMF being induced in the coil. Okay, we're then asked we're asked to look firstly at a graph, okay, of a sinusoidal graph of output. My apologies for future reference. I did do this in pen and then realized after I'd made a mistake. This is, I suppose, a lesson in using a pencil. Okay. We're going to come back to looking at this in a later question. We're told firstly that the average power output of the generator is 8.5 times 10 to the 5 watts. Okay, calculate the root mean squares. We're on RMS again. That's down here. Well, we know that the power out is simply the product of the RMS currents and voltages, and that the RMS is linked by 1 over root 2 to the peak. Why do we want that? Well, we actually know the peak in this case, which is 25. And being very careful to remember 25 kilovolts, not 25 volts. So we want to calculate the RMS current, which is the sort of aim of the game here. Okay, we can substitute our RMS, VRMS that is, by the peak divided by root 2, and simply rearrange. We'll bring the root 2 up, we'll bring the V0 down, and we end up with the current in the RMS is root 2 times P divided by V0, which comes out with a value of 0.48 amps. Okay. Question 9c is one that always trips people up. Okay, we're asked, the voltage output from the generator is stepped up before transmission. Estimate the factor by which the voltage has to be stepped up. Now, a thing to remember here is that whatever the voltage steps up, the current steps down. So if voltage steps up by a factor of 10, current will step down by a power of 10. Now, why is that important? Well, the power lost is proportional to current squared. So anything that the current is doing, we'll square it, and that will give us an estimate of our lost power. So we're really doing a sort of a bit of a chain reaction here. We're thinking about the effect on voltage, and then the effect on the current, and therefore the effect on the power which is lost. Okay, so if power reduces by a factor of n, if we've got this I squared relation, then I is going to go with the square root of that because P goes with I squared. And in this case, our n is 2.5 times 10 to the 2, 250. So therefore, if we want to know the factor by which our current needs to be stepped down, then we need to take the square root of 2.5 times 10 to the 2, which is 15.8, which is around about 16. Okay, in other words, that is the factor at which the voltage needs to get stepped up. This all comes from the fact that our energy conservation, remember, P equal to IV. Okay, and that will tell you the factor by which voltage goes up and current goes down. Last one, deep breath. Frequency of the generator is doubled with no other changes being made. Draw on the axis the variation with time of the voltage output. Let's go back. Now this is where I've drawn it on. Again, my apologies for the terrible drawing. Okay, first thing to pick up on is that if we double the frequency, okay, we're going to halve the period. So the previous period was 20 milliseconds. Okay, my new one is going to be halved, and so therefore we're going to go from 20 to 10. So there's a mark there for getting the 20 to 10. The bit that people forget about is the fact that also the EMF will also be increased, and actually it will get doubled in terms of its peak values. Okay, if we do a little bit of looking into the maths of this, what you'll see is there's a proportionality with F, or also proportionality with omega in the EMF. And this comes with the fact that we differentiate cos theta with respect to time. That therefore means your amplitude of your signal should double. So not only does it go to a higher frequency, it has a higher amplitude. So 1 mark for frequency, 1 mark for amplitude. That concludes the amazing journey through our mock. Okay, please do take the time to watch these videos carefully, watch them again and again, make sure you're happy with the concepts involved, and then we'll get going from there. Excuse the update, Adobe. I look forward to talking to you about this in class.